Maths educational video. Geometrical meaning of first order partial derivatives. In this video, we are going to learn the notion of a derivative for a function in two variables, say x and y. We first recall the definition of a derivative for a function in one unknown. Here we have a graph of a function fx. We take a point A on the graph and we draw a tangent line. The gradient of this tangent line is known as the derivative of the function f, denoted by f prime a. And here's the mathematical definition of a derivative. And keeping this in mind, we would like to extend the notion of a derivative to a function in two unknowns, say fxy. If we try to define derivative using tangent lines, we will face an immediate challenge. For any point P lying on the graph of a function of two unknowns, which is a surface, we can draw infinitely many tangent lines. So we will not be able to define a unique derivative if we use the concept of tangent lines to a point. What we notice is that every tangent line actually corresponds to a particular vector or directional vector on the xy plane. So here is one such tangent line in red. If you were to project this line onto the xy plane, you get this vector. So it looks like to define derivative for a function in two variables, you will first have to specify a direction vector on the xy plane passing through the point AB. This directional vector will then give us a unique tangent line to the surface passing through the point P. So this idea will take us to the concept of partial derivative. We first treat y as a constant and allow x to be a variable. And essentially, y equals to a constant means the directional vector is one that is parallel to the x-axis. Because on this line, the y coordinate is always equal to b. And graphically, in the three-dimensional space, y equals to b is a vertical plane. And this vertical plane will intersect the surface along a curve, which is the green curve. And on this curve, because y equals to b is a constant, the equation of the curve is now given by z equals to f of xb. So you notice that this is actually a function in one unknown, z versus x, because y is now a constant b. And we can now draw a unique tangent line passing through the point P. And the gradient of this tangent line is defined to be the partial derivative of f with respect to x. With respect to x because x is the variable, y is a constant. And notation wise, this is how we write partial derivative, f subscript x, to mean we are differentiating f partially with respect to x. So this is a geometrical meaning of partial derivative with respect to x. Obviously, we can do likewise for partial derivative with respect to y. But this time we have to fix x. So let's say we let x equal to a. Again, geometrically, x equals to a is a vertical plane, and this vertical plane will intersect the surface along a curve. The equation of this curve is of the form z equals to f of ay. So it's a function of one unknown. Z is the dependent variable and y the independent variable. On this curve, we can draw a tangent line, the line in green. And the gradient of this line is the partial derivative of f with respect to y. And the notation, it will now be f subscript y, to denote that we are differentiating f partially with respect to y. Finally, another notation is to write df dx instead of f subscript x. So these are two commonly used notations.